Heat Part 3. In this section, we are going to learn specific heat capacity. By definition, specific heat capacity of a substance is the energy needed to increase its temperature by 1 degree Celsius per 1 kg of mass. For example, the specific heat capacity of water is 4,200 joules per kg per degree Celsius, which means that we need 4,200 joules of energy in order to raise the temperature of 1 kg of water by 1 degree Celsius. Now, let's denote specific heat capacity by the symbol small letter c, energy needed by the symbol E, the increase in temperature by the symbol delta T, and the mass by the symbol M. In the table, let Cw be the specific heat capacity of water, which is 4,200 joule per kg per degree Celsius. And the mass of water is 1 kg. And the change in temperature, the rise in temperature is 1 degree Celsius. Then the energy needed by definition of specific heat capacity of water, which will be 4,200 joules. Okay. If now we increase the temperature of 1 kg of water by 2 degrees Celsius, the energy needed would be 4,200 times 2 joules. If now we want to increase 2 kg of water by a temperature of 2 degrees Celsius, the energy needed would be 2 times 4,200 times 2. If now we want to increase m kg of water by a temperature of delta T, the energy needed would be m times 4,200 times delta T. If now we have a substance of specific heat capacity of C and its mass is m, and we want to increase its temperature by delta T, then obviously the energy needed would be m times C times delta T. As a result, we have E would be equal to m times C times delta T. Therefore, we can write E, energy absorbed by a substance, equal to m C delta T. This equation is very important. Next, let's look at the meaning of power. By definition, power is the weight of energy transferred. For an electric heater of power, for example 100 watts, W means watts. Okay. For an electric heater of power 100 watts, it means that it will consume 100 joules electrical energy in 1 second, and the energy will be converted to 100 joules of heat energy. That means in a time of 1 second, 100 joules of heat energy will be produced. If we let P be the power of the heater in units of watt, T be the time of switching on the heater in a unit of second, and E be the heat energy released by the heater. the relation between E, P, and T would be E equal to P times T. This equation is also important. Let's consider the following cases. Case 1. If power is 100 watts and time is 200 seconds, the energy released by the heater will be P times T equal to 100 times 200 equal to 20,000 joules. Second, P is 100 watts and time is 2 minutes. The energy released by the heater would be P 100, T 2 minutes. We need to change the unit into second. 2 times 60 seconds. Okay? Therefore, the energy released by the heater would be 120,000 joules. Third, if the power is 1 kilowatt and is switched on for 50 seconds, the power is 1,000 watts times 50 seconds. The energy released would be 50,000 joules. Lastly, if the power is 1 kilowatt and the time is 3 minutes, the energy released by the heater would be 1,000 watts times 3 times 60, okay, which is equal to 1x0000 joules. Very often we use scientific notation if the number is too large. This one we can write 2 times 10 to the power 4, and this one we can write in the form 1.2 times 10 to the power 4, and this one we can write in the form of 5 times 10 to the power 4. Lastly, for this one we can write in the form of 1.8 times 10 to the power 5. Very often we use symbol to represent electric heater. Okay, the symbol for an electric heater may be in the form, we draw it like this one, okay, or this one, okay. Now we are going to do an experiment to find the specific heat capacity of water using the apparatus shown in the diagram. First, use a beam balance bond to measure the mass of polyethylene cup M1. Second, add water into the cup and measure the mass of water plus the cup together, which we call M2. Next, record the initial water temperature T1 by using the thermometer, and also record the initial joule meter reading, which is recorded by the joule meter. Next, switch on the low voltage power supply for a time T. After time T, switch off the heater and wait for a time of about 30 seconds, and then record the final water temperature T2 and the final joule meter reading E2. Since the joule meter measures the energy released by the heater, therefore the energy released by the heater during the experiment in the time T would be E equal to E2 minus E1, the final joule meter reading minus the initial joule meter reading. Also, the mass of water being heated in the experiment is M. M is equal to M2 minus M1. And the temperature rise of the water in the experiment is delta T equal to T2 minus T1. Let us let Cw be the specific heat capacity of water. In this experiment, the energy absorbed by water is EW equal to mc delta T. If we have the following assumption: all the energy released by the heater is equal to the energy absorbed by the water, that means there is no energy lost to the surrounding. Then we will have E equal to mc delta T, okay, or E2 minus E1 equal to M2 minus M1 Cw T2 minus T1. Therefore, we can find the experimental value, okay, the experimental value of specific heat capacity of water Cw equal to E over M times delta T. Okay. The true value of Cw, true value means 理論上嘅結果。The true value of Cw is 4200 Joule per kg per degree Celsius. However, in the experiment, very often we find the experimental value of Cw, which is very often larger than the standard value or the true value of Cw, which is 4200. Do you know why? The main reason is that the energy released by the heater is in fact not all this energy released by the heater is absorbed by the water. Okay, there is still some energy lost to surrounding. We say lost to surrounding. Okay, we say heat loss to surrounding. Okay, due to temperature difference. Also, some energy will be absorbed by the porous film cup. Okay, the cup will also absorb heat energy. And the thermometer, how about the thermometer? It will also absorb energy. As a result, the energy released by the heater would be in fact greater than the energy absorbed by the water. In this case, the temperature rise, okay, the temperature rise of the water would be smaller than our expectation, okay, would be smaller than that found in the experiment, okay. Therefore, the value of specific heat capacity of water found in the experiment would be larger. That is, the temperature rise is a bit smaller than expected. Therefore, from this formula, the specific heat capacity of water found in the experiment would be higher. To reduce the heat absorbed by the porous film cup, we should choose a cup with small heat capacity. Also, the stirrer in the experiment is important. We should use the stirrer to stir the waters frequently during the experiment to ensure uniform temperature of water.